So the reason that we can use the negative log of the acid concentration to solve for strong acids and strong bases is because they dissociate 100%. And we know from previous screencasts that when we look and we put a weak acid-base pair in water, they don't dissociate 100%. And so you have two things present that can contribute to the pH. You have a concentration of your base and a concentration of your acid. So when we identified the conjugate acid-base pairs, right, let me do this differently. When we identified these, we said, look, this is the conjugate acid, right? And this is the base as this is written. But we know that NH3 and NH4 plus are what we call a conjugate acid base pair. We can identify that because the only difference between them is that they have an additional H plus, right? That's it. And it's important when you're identifying these that the acid always has one more proton than the base. That's how we identify them. So if we want to figure out the pH of a weak acid-base pair where it doesn't dissociate 100%, we have both these things present in solution, we need to take both of those things into account. And so to do this, we use the Henderson-Hasselbalch equation. So the Henderson-Hasselbalch equation is right here for you, and the pH of a solution like this would just equal the pKa plus log of the base over the acid. And so again, the acid has one more H plus than the base. So we would put, when we looked at this, if we were to identify it, we said, okay, hey, look, the acid is here and the base is there. This is colloquially shown as HA is the acid and A minus is the base because you've lost a proton to get the base. If you go out and you look around on the YouTubes, you are going to find sometimes a different formula for this where there's a subtraction and this is flipped, or there might be a different sign. You can use whichever one you want. I personally like this one the best because when I look at it, first off, I get to add, and I like adding better than subtracting. It just seems more positive to me. And then the other thing I like is this kind of forms a triangle right here. And so it's easy for me to remember that the smaller space taker upper is going to be the base on the top because it has one fewer H plus. And so that's how I remember that. If that works for you, that's great. And if it doesn't, then I apologize. All right, so let's go on and do an example problem. So here's an example. It says, what's the pH of a solution that is 0.200 molar in NH3 and 0.300 molar in NH4 plus Cl? Now, it's important to understand that you can't measure out NH4 plus all by itself. So it's going to have a chlorine to balance out the charge, and this is just a counter ion, and we really ignore that, okay? So we're just going to ignore it. Sometimes if you get into a situation where there's one of these that's a minus, you could have a counter ion that is positively charged, okay? But really the important things here are the NH3 plus, or the NH3 and the NH4 plus, okay? And so your first step is to identify them. While we did this on the last slide, I want you to write it on this slide too, just in case you're just looking at this slide when you're going through and doing some homework or you're studying. The NH4 plus is the acid because it has one additional H plus compared to the base. And so we sit here and we say, great. We know Henderson-Hasselbalch. It equals pKa, pH equals pKa, plus the log of the concentration of the base over the acid, right? And so when I do this, I say the pKa is given to me. Now, to solve a problem like this, the pKa either needs to be given to you, but if the Ka is given, right, use negative log of the Ka will get you the pKa, right? So don't forget that. So you might have a question that has both of those. Plus log, and when we come here, we put the base in, that's 0.200 molar, and then we put the acid in, that's 0.300 molar, right? And when I set out to solve these problems, I write the 9.3 plus the log, and the very first thing I do in my calculator is the math here in the parentheses. So I take 0.200 and I divide by 0.3, and that gives me 0.666 repeating, right? And so I'll keep all that in my calculator, and then I hit log, and then I just add it to 9.3. But I like to go ahead and work this number out in case I hit a button that's funny or something along those lines. So in case you're doing this step by step, the log of the 0.666 is negative 0.176. So do follow along with your calculator and check that. And then when we do that math, we get 9.12. And that's the pH of a weak acid-base pair. Now, one of the reasons this is important is because weak acid-base pairs can act as buffers. And when we talk about buffers, buffers are important biologically because they resist changes in pH by neutralizing small additions of acids or bases. So these guys resist changes in pH when acids or bases are added, okay? So basically what happens is a buffer will have a weak acid here in its conjugate base, right? Or a conjugate base in its weak acid, okay? And so we'll have some combination of those two things. What happens is, and so this is an equilibrium in the solution, if you add a base. So when we look at this, we have come here and we have added this base. When we add the base, it will react with the acid of the buffer and form more of this kind of weak conjugate base. If we add a acid, like a strong acid to it, not what I wanted to do. If we add a strong acid to it, like right there, what it's going to do is it's going to react with a weak base and form more weak acid. And this keeps the pH in a solution from fluctuating too much. And that's very important for us biologically, because if the pH fluctuates, then the proteins in our body won't function the same way. Now, and there's lots of things that are buffered. When we talk about buffers and resisting these changes in pH, there's a pH range, okay, where buffers work the best. And that's called the buffer range. And so the buffer range is just the pH range where buffers give the best pH protection, okay? And the buffer range for each buffer is generally a pKa plus or minus 1 unit, right? So, for example, if the pKa is 9, the buffer works well from 7 to 9, okay? The reason this is because when works well from 7 to 9, I want you to put works well from pH equals to 7.9. When the pH equals the pKa, you have equal amounts of the acid and the conjugate base. So because you have equal amounts of the acid and the conjugate base, that means that if you add a strong acid, there are plenty of molecules of the base to react away and keep that pH neutralized. Or not neutralized, that's not a good word. It'll keep that pH in the same range, okay? And so when we get too far away from the pKa, let's say we go to a pKa of 3, it's very acidic, you end up with more of one of these than the other. And because you don't have very much of this molecule, if more acid was added, there wouldn't be many of these molecules to react it away. And so that's why each buffer has a certain pH range. And you can choose the buffers based on what you want. Now, the other thing that you'll hear people talk about besides buffer range is buffer capacity. And buffer capacity, right, is just maybe the quantity of acid or base that a buffer can neutralize while maintaining pH within the desired range. And generally, it's proportional to component concentrations. So the more, so if you look here, this is a little buffer system. If it has a very low concentration, then there's not enough molecules to help kind of neutralize that acid or base. And then if it gets higher, there are more molecules present that can react with the acid and base, and they can keep the pH from fluctuating too much. Now, so then the question may be, well, why don't you just have a super high buffer concentration? Well, if you get too high, then sometimes the ions of the buffer can prevent the reaction that you're interested in. So you sort of have to have a sweet spot. An illustration of buffer capacity is shown here. And so what we see, this is for acetic acid and acetate. So this is an acetic acid acetate buffer concentration, and it has a pKa equal to 4.75. Now, the red line here indicates the pH change that would occur when 1 milliliter of 1 molar HCl is added. And so what you see here is when the initial concentrations of the acetic acid and acetate are about 1, the pH change that occurs is really negligible, right? However, if you add, when you come down here and look at this buffer that's only 0.015 molar concentration, and you add HCl, you see a pretty significant decrease from a pH of about 5 to a pH of 4. And then the blue line illustrates the same thing, just with NaOH. So at a higher concentration, when NaOH is added, the pH doesn't vary very much. But at a lower concentration, we see a big variation, right? So the higher the concentration, the better the buffer is, or the better it works. Now, maybe the burning question in your heart is, well, how do I make a buffer? And there are 3 ways to make a buffer. The first way is you add a conjugate base to a weak acid for that conjugate acid-base pair. The second way is to add a strong acid to a weak base, because that weak base will react and form the conjugate weak acid. So now all of a sudden you'll have acid-base pairs. And then the third way is to add a strong base to a weak acid. All right, so this ends our lecture on buffers. If you have any questions, please feel free to stop by my office.